so I have this setup that I have marks on the x-axis, which is kind of weird. Usually we try to keep something like that on the y-axis, but in this one, I'm going to do that. Now, let's suppose towards a very right side, bilkul extreme right way, marks are going to be super high, right? So would you expect a point like this to be a more practical value or a point like this to be a more practical value? In दोनों में से कौन सा point हो तो you would think हाँ ये ज़्यादा realistic है. So what does this point represent? This point represents that you have very high marks but very few students, and then you also have very high marks but this time the students are more who are scoring that. Which school or class would be a good one?
The upper one.
The upper one, yeah, because उसमें ज़्यादा students के, like the portion of students who have gotten high marks is high. Let me say, where do you expect the average marks to be? Let's suppose ये average है मेरी. So would you expect a greater number of students to be on the average or a lower number of students to be on the average?
Sorry, greater.
Greater number of students. So we would expect a higher number of students to be somewhere here, right? So the number of students who have this many marks, the average marks, we are going to expect them to be there. And we may expect, like, let's suppose nobody failed or nobody got a 0 mark. So then origin is our starting point. So let me try to connect them. I will expect a curve like this, or I can also expect a curve like this. Turns out, realistically speaking, in most systems, we have this setup. In most systems, we have this, that it starts at 0, goes like that. And in fact, if I continue this, it goes like this. It never fully reaches 0. कभी ऐसा नहीं होता कि बहुत ज़्यादा high marks पे कोई student नहीं होता, जिसको हम कह देते हैं कि जी percentile गिर गई, percentile ज़्यादा हो गई and all that. बहुत high marks में भी कोई ना कोई एक बैठा होता है जिसने 100 लेने हैं और सारों की percentile उसने खराब करनी है. होता है ऐसे, which is this one student which is at this higher level, world top कर रहा है बैठ के. So this is more of a realistic thing. This is how the distribution works. Wherever you distribute things to individuals, वहाँ पे usually इस तरह का होता है. Go on, wealth distribution देख लो. There is going to be somebody who has a very high net worth, or the number of those people will be very low. Y-axis पे बहुत नीचे होगा, but x-axis पे वो extreme पे होगा. And people with average income will be somewhere here towards the hump. And this curve is a very, very powerful curve because it explains so many things. It explains mark distribution in students, kisi school ke andar. It explains wealth distribution for people. It explains the chances of somebody getting COVID. People who are going to get COVID ke zyada symptoms ya zyada healthcare on the very right side and all that. Whenever you want to distribute things to people, there is a high chance that they will have something like this, or a graph like this might come. I'm not saying that hamesha aisa hota hai. There are many, many different distributions, 6 or 7 come to my mind, but this is a very powerful distribution. In fact, the relevance of this distribution right now is that this tells us कि यही हम students की बजाय particles ले लें, and यही हम marks की बजाय energy दे दें. And this is a realistic picture of how energy is distributed in a closed system. Particles have this energy, and there are few particles with very high energy, जो इधर होते हैं, and they are the ones that evaporate. एक liquid में, if you have this thing, let's suppose you need this much energy to evaporate, like this much energy to evaporate. So which particle? So this is the energy for evaporation. Let me call it A. So tell me, particles on the right side or the left side, which ones can evaporate now?
The right side.
Right side, because why is that?
Because they have more energy on the right.
Just more energy or greater energy than this required level?
Yeah.
Right? They have greater energy than this required level. And these are the particles that will evaporate. And I can shade it like that. In fact, not just this, there is in any chemical reaction a level of energy that we need for things to actually react, and that is EA, activation energy. They need activation energy if they want to react, and things on the right side of this will be able to react. What about particles on the left? They have energies that are less than this activation energy. So no matter what happens to it, no matter how many times it collides, it is not going to be able to react because उसके पास वो energy नहीं है. Imagine this was the passing marks of any student. So जो इसके right side पे होगा वो pass होगा, जो left side पे वो pass नहीं होगा. Now let's suppose what we do is we give these particles a very high energy, सबको high energy दे देते हैं. So what will happen to the average?
Sir, it will move to the right.
Exactly. The average is going to move to the right. By the way, realistically, average is never on the hump. It's slightly below the hump. मतलब इधर करके average होएगी. But as you heat this thing, as you provide them more energy, more particles are going to go towards the right side. वो इस bridge को, this activation energy वाले bridge को cross करना शुरू कर देंगे, उनके पास energy ज़्यादा आनी शुरू होगी. So probably they're going to be somewhere here. The hump is moving forward. It's going to probably be somewhere here, but also, जो हमने शुरू में बात की थी, if you have a better school, then you would expect this curve to be slightly higher here. Because more students with very high marks should be there. मतलब आप Alpha Star Academy में चले जाओ, तो वहाँ पे सारे इस साइड पे बैठे होंगे. Alpha Star is one of the best schools I know of, US में. So the curve would look something like this. It's always a curve, तो थोड़ा सा इसको curve आपने करना है. Now, what is the relation of this curve with the previous one? Can I say that more particles will react here? Yes or no? Can I say that more particles in this yellow curve will react? Successful collision only. Yeah, we can. And the reason for that is that now the activation energy hasn't changed, but now I have this extra yellow portion of particles that have enough energy to react. And that is what happens when you heat things. When you heat them, all of them drive to the right side. Their energy is increased, even though the particle numbers. There are still those particles that have very low energy. And there will always be those particles. But here's the interesting bit. थोड़ा सा यहाँ पे ना मैंने गलत किया है. Reason that this curve goes like this, the best part of this curve is that the area is always equal to number of particles. Which means that if I drive them towards the right, then the height will decrease. क्योंकि मैंने अगर उसकी base increase कर दी तो मुझे height को कम करना पड़ेगा. Just like imagine a rectangle. मैं एक ही एरिया की रेक्टेंगल बनाना चाहता हूं, तो अगर मैं उसको लंबा करूंगा तो ऊपर से थोड़ी सी छोटी हो जाएगी. If I want to keep the area the same. And that's what happens to this curve, that instead of having something like that, it will be something like, okay. So the height is going to go down because more particles are going towards the right, but area remains the same because the number of particles is the same. ज़्यादा temperature पे क्या होगा? If I heat it even more, then there's going to be something like this. More particles on the right side of this. In fact, average भी हो सकता है right side पे चली जाए. And if I keep on heating, that is how it goes. So when you're boiling things, that's what you're doing. You're giving all the particles more energy, and that is how they move towards the right side. Now, we need this to work. We need to understand this. Imagine this was actually, this line was not activation energy, this was poverty line. And this was not number of particles, this was number of people. So the more opportunities you give to them, the more you drive people towards the right side of this poverty line. And it's important to understand this distribution so that we can fix those problems. So it goes beyond just particles. Let's come back to particles. Activation energy is the minimum energy they need to react. And the kinetic energy, the higher they have, the more they have a chance of being towards the right side, which means the more chance they have of reacting by collisions. Okay, so this is a spread of kinetic energy, the velocity of these particles, and the more they are on the right side, the better they are, the more reactive they are. Okay, now if I increase pressure, how does that drive things towards the right side? क्योंकि सीधी सी बात है, उसको ज़्यादा energy देगा तो वो right को जाएगा ना. So when I give them more pressure, they collide with more energy. So उसकी collision इस side पे आ जाती है. Okay, what about catalyst? What does catalyst do? Catalyst तो particles की energy को कुछ नहीं करता. So why is it that with the catalyst they do increase in terms of their rate of a reaction increases? Can anybody define what a catalyst does? होता क्या? Primary function catalyst का क्या होता है?
Sir, a catalyst provides an alternative pathway that requires less activation energy, so more particles can react.
So there is alternative pathway, okay? So it's like a shortcut that it gives with lower activation energy. This is the key part here, lower activation energy. So now more particles can react, which means that what catalyst does is it does not give them more energy, but it pulls this activation energy back. So now you're going to get a lower activation energy. So pick any curve, any of these curves. There is this portion of purple that is being added. Those are all the particles that have been driven over that edge just because we have a shorter, lower energy pathway. That's what a catalyst does. So this catalyst, all it's doing is, अगर आप green की बात कर रहे हो, तो green में green वालों की निस्बत it has added these purple particles in there. आप red की बात करो, yellow की बात करो, no matter which distribution you talk about, a catalyst will provide opportunity to more particles to go over the edge क्योंकि उसने उनका जो basic requirement थी वो बढ़ा दिया, कम कर दिया. Sorry. Imagine एक class है उसमें passing marks 50 हैं और एक class है जिसमें passing marks 80 हैं. तो 50 वाली में automatically more students will pass because the passing requirement is more lenient. Just like that, particles that are able to actually react are the ones that are on the right side of this, that have energies that go on the right side of this. And the reason they do this is because they have enough kinetic energy to react. Now here's the thing. Sorry. There's actually no particle that ever has zero energy. Zero energy वाले particle नहीं होते. There are particles with very low energy. Sure, मतलब आपके पास इस side पे कोई ना कोई particles होंगे, ठीक है? With very low energy. It is possible that you will get some particles here. They are very low energy, but there are also a very few numbers of them. Most of them, जो आपके पास average आते हैं ना, वो इस side पे होते हैं. उनकी energy थोड़ी सी ज़्यादा होती है, उनका number high होता है. Averages are always higher. ठीक है? And in these particles as well as in life, you should try to just be above average. और आप गुजारा कर लोगे. Outlier बनने के लिए आपको इस साइड पे आना पड़ेगा, which is very difficult sometimes. Fair. So here's the thing: the green one has lower temperature, yellow one has higher temperature, red one has even higher temperature. But that also means that the more temperature they have, more the curve goes like this. The curve goes towards the right side, but its height also decreases. That is because more particles have higher energy, higher velocity. The curve now is more broad, ज़्यादा flat हो जाएगी because particles बहुत ज़्यादा right side पे आ जाएंगे. But the area, number of particles that you have, they should be constant. Okay, and that is what this distribution is. This distribution is named after one of the greatest mathematicians of all time, I would say, Boltzmann, German tha, obviously, like all great mathematicians, most of them, I mean, Boltzmann. Okay, so this Boltzmann's distribution or Boltzmann curve tells us the distribution of energies in particles. Now, obviously, if I try to cool this thing, then what will happen? The energies will start going towards the back, which means अब थोड़ी सी cooler energy अगर मैं बनाना चाहूँ तो वो ऐसे करके होगी कि वो higher होगी इधर से और इधर करके होगी. So notice that the height is higher than the previous ones, but it's also towards the left side. And this is lower from here. Now pick any two colors here. We want to compare those two curves. Let's say, pick a color, Meher.
Red.
Red. And pick a color, Sarah.
Yellow.
Yellow. So let's compare red and yellow. What are some similarities in the red and yellow curves that you see? एक तो मैंने आपको बता दिया that they have the same area because the number of particles is the same. They're both starting at zero origin. That's because no particles have zero energy. The difference is pretty clear. Red one is flatter. Yellow one is not that flat. Yellow one is towards the left side more. Red is towards the right side more. Red is for a higher temperature. But there is one crucial point that I want you to focus on. They only intersect at one point. There is one point where the both are the same. उनकी values, उनके number of particles, energy सब same है. But उसके बाद वो कभी intersect नहीं करते. Which means if a curve शुरू में higher temperature वाली नीचे होती है, end पे वो higher होती है. And that's important. The higher temperature curve ends up higher. Okay? Higher temperature curve ends up at a higher level. शुरू में नहीं होगी वो, शुरू में नीचे होगी, उसकी एवरेज भी आगे बढ़ेगी. It always ends up at a higher level, and that is why it's important. Because अगर मैं एग्जाम की बात करूं तो एग्जाम में they are going to give you a curve or they are going to give you a graph and ask you to draw a curve for energies, and then they're going to ask अच्छा टेम्परेचर बढ़ा दिया अब बताओ. So just remember this: higher temperature curve ends up higher. And why is that? Because the average has gone higher. Really, it's that simple. Baki, shaded area is important because you want to be able to explain how that is relating to why some particles react and most of them or many of them don't. Why some particles evaporate and most of them don't. Why does boiling make more particles actually change to gas? Because you're just driving them forward. What does a catalyst do? It brings activation energy down. So now more particles are in that shaded area. So they're able to collide with energies that you need. There is a greater proportion of these molecules or these particles, jinki energy is greater than, it exceeds activation energy. And that's how rate of reaction is higher. Clear? Let's do a question. There's a reaction happening at 30 degrees Celsius. Draw a Boltzmann distribution graph for the energies of particles there. On your notebooks, go on. Now, the temperature is increased to 50 degrees Celsius. What will be the new curve now?
Sir, what did you say? Sorry, my internet cut.
I'm saying that there is the same reaction happened at 30 degrees Celsius and same reaction happened at 50 degrees Celsius. On the same graph, draw the two curves. Done, everyone? So your answer should be something like this. So you will obviously draw an axis like this. You will have energy on this axis. You can put it in kilojoules maybe. And on this side, I have particles. These could be in moles. Now, the first curve for lower temperature will be something like this. This is for 30 degrees Celsius. The second equation should be, second curve should be for a higher level. So it might be something like this. Now, what will your curves be judged at? Number one, the 50-degree curve should have a lower high point. मतलब ये maximum point इसका ये यहाँ पे है, तो इसका maximum point उससे नीचे होना चाहिए. So this should be lower. They should both intersect at just one point. And the 50 degrees Celsius, the higher temperature one should be higher than the purple one. It should end up higher. Higher temperature curves end higher. Now show the activation energy. Okay, let's suppose this is activation energy. Your choice, very quick. And then a 2-mark question comes that explain how raising the temperature increases the rate of reaction using this curve. So in your answer, you should refer to this shaded area, the extra shaded area that we have. More particles are on the right side of activation energy than they were before. All right. So this is usually a basic question of 4 or 5 marks that they ask you.
Sir, आप repeat कर सकते हैं जो activation energy वाला.
So why does increasing the temperature increase the rate of reaction? And the answer is that the particles on the right side of activation energy, particles that have more energy than activation energy, have increased because the shaded area of those particles has increased. शुरू में आपके पास shaded area was just this one. So this is the number of particles, the gray ones, that are able to react. But now with increased area, with increased temperature, this yellow portion is also including those particles. So there are more particles that have energy that is greater than activation energy. So now they are able to react, collide at the same time, or per unit time, more collisions are happening. So the rate is faster. There's the same explanation as O levels wali, but you're just referring it to energy distribution in particles, and you now know better than O levels कि basically energy किस तरह distribute होती है. Suddenly jump नहीं होता किसी के पास कम energy, किसी के पास ज़्यादा energy, just like in life. Okay, तो ये हो गया हमारे पास Boltzmann distribution. अगला question 1 mark का, show how on the graph show how a catalyst increases the rate of reaction. So to answer that, you should simply draw a new activation energy, call it the catalyzed activation energy or something. And you should show that now you have more particles that are on the right side because activation energy is lower. So O levels mein hum ek graph karte the, which was this one. And we would say that when you add a catalyst, it goes like this. And that is the same as this one. कोई इनमें conflict नहीं है. The activation energy was referred over here. यहाँ पे हमने activation energy with respect to energy of the particles बता दिया. Basically ये जो O levels वाला graph था ना, ये हम बच्चों को इसलिए बताते थे कि बेटा reactant की ये level है, product का ये level है, enthalpy वगैरह के लिए. This is good for enthalpy. The Boltzmann graph is not good for enthalpy क्योंकि उसमें enthalpy की बात ही नहीं हो रही. Energy has gone away, and by the way, that energy that goes away, that is one reason why the graph comes lower. उसकी height कम होती है. That is one reason, but obviously not the entire reason. Okay, sorry. So that is rate of reaction. Now let's talk about catalysts. We know catalysts increase rate of reaction by providing alternative pathway that has a lower activation energy. Three things: increases the rate, different pathway with lower energy, activation energy. But catalysts come in two ways. There are catalysts that are in same state as the reactants. They are called homogeneous catalysts. And there are catalysts that have the different state as to what they're reacting with. They are called heterogeneous. You know heterogeneous catalysts. You have seen ammonia में iron use होता है when you're making ammonia in Haber process. Iron is a solid. Nitrogen, hydrogen, they are reacting, they are gases. But iron still provides a way for them to react faster. And that depends on a process called adsorption. What is adsorption? It is adhesion plus absorption. Two things, we bring them together and make adsorption. Okay? And homogeneous catalyst क्या होता है? Collisions. वो एक के साथ collide करता है, फिर उसके साथ collide करता है. एक bond बनाता है, दूसरी bond बनाता है, फिर उनको join कराता है. For example, acid. आपने पढ़ा होगा esters को break down करने के लिए acid use होता है. हमारे stomach में HCl होता है. खाना भी वैसी paste सा बन जाता है. और HCl भी liquid सा होता है, उसके ions होते हैं. They are homogeneous. They are all in the same fluid state. And that happens because of collision. They're in the same phase. The word we'll use is not state. We'll say they're in the same phase. So right now we just need to know examples of this. Okay. So two examples, homogeneous catalysts. The role of nitrogen dioxide in oxidation of SO2, sorry. So in the air, SO2 converts to SO3 because nitrogen dioxide is able to provide oxygen to it. So nitrogen dioxide is a catalyst. So हमारी गाड़ी के इंजन में nitrogen dioxide बनती है, वो हवा में जाती है. It catalyzes the production of SO3, which causes sulfuric acid to make, and then acid rain होती है. तो गाड़ी अच्छी होनी चाहिए. गाड़ी में engine should perform well so that nitrogen dioxide वगैरह ना हो. But more than that, engine का कसूर नहीं. Engine has high temperature, nitrogen and oxygen come from the air. We should have catalytic converter. With catalytic converter, it will make sure no nitrogen dioxide, nitrogen monoxide, they don't exit and they don't damage the environment. Second role that we need to know is there are two negative ions. Imagine this. I have two negative ions. and I want them to react with each other. There's the iodine ion, which is negative, and there's the peroxydisulfate. Peroxydisulfate ion. Both negative ions. I want them to react. Why reaction happens because of collisions. A negative thing is unable to collide with a negative thing. It's going to repel it. The repulsion is so strong, it's like 18,000 times the force of gravity that is currently pulling you down towards the center of the earth. That is the strength of this repulsion. So फिर क्या होता है? We get iron 3 catalyst. Iron 3 is ion positive. It bonds with one. उसको जाके दूसरे के साथ bond कराता है. Makes a match. So it acts like the रिश्ता वाली आंटी. Don't judge me. People can be as repulsive as two negative ions. So this is homogeneous catalysis. Now, for the heterogeneous one, you already know it. You know iron in Haber process. You know transition metals in catalytic converter, rhodium, platinum, palladium, and lastly we have B2O5 in contact process. Now this part, I'm not spending much time on it because ये सिर्फ याद करना है. You can just read about it in your book. That's it. We're done with this reaction kinetics.